Another method is improved Euler method or Heun's method. In which in this method, instead of using a slope of the line here or a slope of the line in the next iteration, we use combination of them. And how it works, it says x in the next iteration is going to be x in the current iteration plus 1/2 of h times f in tk and xk, which we already have them, and plus slope in the other one. However, we don't know what is x in the next iteration, and because of that, we do this. We say f at tk plus 1, which we know what is the time then. And because we don't know what is xk plus 1, we use an estimation of it, which we can find it using just forward Euler method. So it's going to be xk plus h times f tk and x k minus 1. So all of these together is going to be an estimation of x k plus 1. So I can put it here to find an estimation of the slope in the next iteration and average it with this with the slope at the current point. And then after finding the average, now I can use it in an equation which is similar to the Euler method. Okay. This one is computationally it's much less expensive than backward Euler method, and it is pretty robust. The most sophisticated one is Runge-Kutta method, and there are different versions of this Runge-Kutta method. Actually, the Heun's method is a type of Runge-Kutta method as well. But the most sophisticated one, ODE45, is the way which I'm going to explain it. So Runge-Kutta method. Here we find x in the next iteration as follows. xk plus 1 is going to be x in the current time plus 1/6 times h times capital K1 plus 2 times capital K2. This K is different than this K. And plus 2 times capital K3 plus K4. And for any of these K's, we have an equation. K1, or capital K1, is f at the current time and current x. And K2 is f in the current time plus 1/2 of the step size. And instead of x, we are going to use x at current time plus 1/2 of the step size, h, times K1. And K2 and K3 is going to be f at current time plus 1/2 of h, and x at the current time plus 1/2 of h times K2. And finally, K4 is going to be f times t, f at t k plus h and x k plus h times k3. So at any time iteration, I need to calculate k1, k2, k3, and k4, and then plug them back here in this equation to find x in the next iteration. There are different versions of the Brand-Kata method, and this is one of them. And each one is appropriate for some specific type of equations. But in general, it's a very powerful and efficient method to solve ordinary differential equations.